Okay, so number 14 here on the review, they're asking you to do a whole bunch of stuff right here, but essentially they want us to end with a pretty decent graph of what this function looks like here. So trying to go in order of their directions, the first thing they're asking us to find is the x and y intercepts. This is something I never talk about with you guys very much, but you've definitely done it in the past. Anytime you want to find an x-intercept, what you're always going to do there is set y equal to 0 and solve. So that means that we're going to take 4x plus 20 to the 1/3 power, set that y value equal to 0, and try to solve that. So cubing both sides, that'll make the right side still just 0, so we'd get 4x plus 20 would equal 0. Subtracting the 20, we get 4x equals a negative 20. And dividing by 4, we're going to get x equals negative 5 for your x-intercept right there at the 0.50. To find a y-intercept, we're going to go the other route right here. We're just going to set x equal to 0 and solve from there. And that one actually is going to be easier. So what we're doing for a y-intercept is we're essentially just finding f of 0. So I think we can do that pretty quickly in our heads, guys. 4 times 0 is going to be 0 plus 20. This is going to be 20 to the 1/3 power, which is the cube root of 20. That doesn't come out to be anything nice. So let's think about that for a second, and I'm really not that worried about getting this thing super accurate. The cube root of 8 would be 2, the cube root of 27 would be 3, so this number is going to be somewhere between 2 and 3, and if I had to guess, maybe a little bit closer to 3, but it doesn't really matter. So that's how we would use our x-intercept and our y-intercept to get a little bit of information about what this graph looks like. Next thing it's asking for after those intercepts, x-coordinates of our critical points. So this comes from our first derivative. F prime of x is going to equal, taking the derivative of f of x here, we're going to get a 1/3 times a 4x plus 20. Dropping the power by 1 is going to be a negative 2/3, and then times the derivative within by the chain rule is going to be a 4 there. So this is not pretty at all, but it looks like that is going to be a 4 over, here we go, guys, we now have a 3, that's the 1/3 and the 4 put together, and then, well, this doesn't work out very nicely, I'm going to leave this as a 4x plus 20 to the 2/3 power. Ugh. Now, when we would set that equal to 0, which is what we would normally do to find the x-coordinate of a critical point, I want to remind you guys that what's going on here is that we have a division problem set equal to 0. The only way that the quotient of a division expression will ever equal 0 is if your numerator is 0 and the denominator is something else. Well, that numerator is a constant value of 4. So that means it's impossible to take 4 divided by any number and get 0 for your result. So there is no x value here for which the first derivative will equal 0. There might be, however, an x value for which the first derivative is undefined. That's the other way that a critical point can occur. And a fractional function, a rational expression, would be undefined anytime your denominator, 3 times 4x plus 20 to the 2/3 power, anytime your denominator is equal to 0. And in this case here, guys, we would divide both sides by 3, still getting us a 0 on the right side, and then take both sides to the 3/2 power, which would still get us a 0 on the right side. So basically, if that 4x plus 20 is equal to 0, that'll give us what we need right here. So we'd subtract the 20, divide by the 4, and we would get x is equal to negative 5. And that is the one and only critical point that we have here. That is the only value of x that makes your first derivative here either 0 or undefined. Now again, reading my directions carefully, they asked for the x-coordinates of the critical points, not the y-coordinates. So technically I'm done with what they asked for right there, but you'll notice we already knew, because of this x-intercept right over here, that the y-coordinate of that point is 0. So negative 5, 0 is the only critical point that we have there. Now, they did ask us to go further, though. Open intervals where the function is increasing and decreasing. So this is where I would make my little sign chart right here. Pick an x value less than negative 5. How about negative 6? And something greater than negative 5. How about 0? That's probably the easiest way to handle that. And let's put those two test values into our first derivative, f prime. So when we put in, let's see, I'm going to focus on this version of the derivative right here. When we put in something like -6, 4 times -6 would be -24, plus 20 would be -4. But we're now taking a negative number to the 2/3 power. Now the way I would do that is I would take the cube root of that negative number first, which would get me a negative result, but then I would square that negative result, which would turn it positive. And then times 3, still positive. 4 divided by that positive number, still positive. So f prime is going to be positive here, which means that our function has to be increasing on this interval here from -infinity to -5. And now, this is interesting, this is why you test things, guys. When we look at the second interval now, and I'm choosing 0 as a test value, the exact same thing is going to happen. 4 times 0 plus 20 is going to be positive. A positive number to the 2/3 power is still positive. Times 3, still positive. 4 divided by that positive number, still positive. So despite what you might have assumed here, f prime remains positive, which means the function is still increasing. So they asked here for open intervals where the function is increasing and decreasing. We could say that this function right here, guys, is increasing basically for all real numbers on the open interval from -infinity to +infinity. And that's an important piece of information to have here as well. And since it's increasing for all real numbers, we know that it would never be decreasing. Now they want us to go a little bit further. X-coordinates of the inflection points, and then intervals where it's concave up and concave down. So shifting from the first derivative now into the second. So I'm going to put a line right here, and let's take a look at where we were here. I'm going to take a moment and just kind of rewrite what we had here for f prime of x. And probably the better way to write that would have been to put the 4 and the 1/3 together to make a 4/3. But I'm going to leave this now as 4x plus 20 to the -2/3 power, because my second derivative then will be pretty easily handled with the power rule and the chain rule after that. So the -2/3 times the 4/3 out in front is going to give us a -8/9 times the same base, 4x plus 20 to the -5/3 power, and again, times the derivative within, which is still a 4 there. So that's going to be, yeah, nothing's going to cancel there, -32/9. Yeah, I'll write that the way I wrote the last one right here. I'll make a bigger fraction out of that. And then with the 9 on the bottom, I'll put the 4x plus 20 to the 5/3 power. Not the prettiest way of writing it. Now to find an inflection point, or a potential inflection point, we would set the second derivative equal to 0, but we have the exact same problem here that we had up here a couple minutes ago. This fraction has -32 in its numerator. That will never equal 0, but it might be undefined once again if the denominator was set equal to 0. So I'm going to do the same thing here really that I ended up doing on my first derivative. We're going to take the denominator, 9 times 4x plus 20 to the 5/3 power, set the denominator equal to 0, and solve. But I think you guys see what's going to happen here. Dividing by 9, the right side is still 0. Then we would take both sides to the 3/5 power, the right side would still be 0. So we would simply set 4x plus 20 equal to 0, and once more, we're going to get x is equal to -5. So what we have right here is a potential point of inflection. All right. Now, by the way, one thing you might notice here, we got x equals -5 as a critical point. And critical points are very often either a max or a min. But in this case, because the function never changed behavior, or we could say its first derivative never changed sign, that critical point was neither a max nor a min. And very often, when you have a critical point that's neither a max nor a min, it ends up showing up again as a point of inflection. Now, let's not assume, let's test that. So once more, I'm going to pick something to the left of -5, like -6, and something to the right of -5, and we'll pick 0. And we're going to put these values now into the second derivative, which is probably best evaluated right here. And let's see what happens when we put in something like -6. 4 times negative 6 is negative 24 plus 20 is negative 4, so a negative number. The cube root of a negative number is negative. We'll then take that to the 5th power where it'll stay negative. Times 9, still negative, and negative 32 divided by that negative number means that our second derivative here, f double prime, is going to be positive, and we are concave up on this interval from negative infinity to negative 5. Okay, what happens when we put in 0? 4 times 0 plus 20 is positive. A positive number to the 5/3 power is positive, times 9, still positive, and negative 32 divided by that negative number now means that f double prime is negative, and we are now concave down on this interval right here. So again, they asked us for intervals where it was concave up or concave down. So now I think, let me just write this over here, that this function here is concave up on the interval from negative infinity to negative 5. And then we can say that it is concave downward on the remaining interval from negative 5 to positive infinity. Okay. They wanted x-coordinates of the inflection points. We found that right here. I guess I should probably list that out. Point of inflection at x equals negative 5. Might have made more sense if I wrote that above my intervals of concavity, but same difference right there. Gotcha. Okay, got all that. Relative minima and relative maxima they've asked us for as well. It's odd that they asked for that now, but because we had no change in behavior right here, we can say pretty clearly, guys, that we have no relative max or relative min. Okay, so all of that follows from the work that we did up above. So with all of that now, they want us to use that information to sketch the graph of the function, and there really isn't a whole lot to this one. We know that this function is always increasing, although it does level off just temporarily with a horizontal tangent there at x equals negative 5. But we do know, because of this sign chart and this information over here, we do know that the function changes concavity. It begins concave up and ends concave down. So we're dealing with a function then that is increase. Let's try that again. We begin with a function that's increasing but concave up, and then it ends increasing but concave down, and it's going to look something like that. And I hate to say this, but if we went all the way back to Algebra 2 and we thought about what it is that we're dealing with right here, this is a cube root function of 4 times the quantity x plus 5. Yeah, this actually is what a cube root function usually looks like. That plus 5 would move your starting point from the origin 5 units to the left, and the cube root graph just basically follows a shape that looks something like this. So that's a lot of work right there. That's what number 14 looks like.